Hello and welcome back. Section 2.6, we get into mathematical models. And we work on the idea of building functions. So we're going to let point P be some ordered pair xy on function f of x is 2x squared plus x plus 1. So we're going to find the distance between P and O being the origin. With respect to variable x. Alright, so we have a parabola and we know it's opening up. Here is the origin at 0, 0. Here is point P at x, y. And we want to describe the distance between them. So hopefully you're remembering back to our work on distance, where we just make a nice pretty little right triangle out of that. So there's our distance. 0 to x is x, 0 to y is y. So distance squared is x squared plus y squared. So, while true, this one doesn't really help us since we want this written as a function with respect to x instead of something in several variables. Well, by substitution, f of x, that's our y, is the same as 2x squared plus x plus 1. So then d squared is x squared plus the quantity 2x squared plus x plus 1 squared. And so that we don't fall into that trap of trying to just square each piece, remember in general a plus b quantity squared does not equal a squared plus b squared. We're going to write out 2 copies of it and distribute. So we have, don't forget to bring along the rest of your problem, so remember this x squared guy coming along as well. And we have 2x squared plus x plus 1 by another 2x squared plus x plus 1. So hang on to that first x squared and then distribute. So first the 2x squared times all 3 terms. So we have 4x to the 4th plus 2x to the 3rd plus 2x to the 2nd. Took care of that guy. Now we'll distribute the x to all 3 terms. So plus 2x to the 3rd plus x squared plus x. And that one's taken care of. And finally we'll distribute the 1. So plus 2x squared plus x plus 1. So plenty excuse me, plenty of like terms to be had here. So distance squared, highest exponent I see is the 4th power, and it was the only one of its kind. So 4x to the 4th, and then I'll look for my cubes. 2x cubed plus 2x cubed, so plus 4x cubed. Then my squares, 1, 2 there, 3 total, 4 total, 5, 6. First powers, 2 of those, and constants, only 1 of those. So the distance with respect to variable x is going to be, usually we would put a plus or minus when we introduce the square root to an equation that did not already have it. But remember, distance is not a negative number. Distance is a 0 or a positive only. So 4x to the 4th inside of our radical plus 4x to the 3rd plus 6x squared plus 2x plus 1. And that's as far as we can take that one. Now, we can have the graphing calculator help us to approximate what that minimum distance might be. So on that one, we put in sort of a placeholder variable. So the calculator works in terms of y's and x's. So in the calculator, we're going to have to call this y1, even though this is not the same as the original variable y from the problem, is equal to our square root of 4x to the 4th plus 4x to the 3rd plus 6x squared plus 2x plus 1. But we can key that in. So clear out any of the older functions you have, put in the new guy. So square root of 4x raised to the 4th plus 4x raised to the 3rd plus 6x squared plus 2x plus 1. So we got that whole thing typed in. We'll close it on up at the end there. And we'll start on zoom 6 and adjust as needed. So the y is, remember, a distance, so notice it doesn't dip into these negatives. So we want to find that minimum distance, so second and calculate. We want the minimum, that is option number 3 there. And left bound, right bound, and a guess. So we're to the left of where it should end, to the right of this bottom piece, and a good guess at the bottom. So the y value is really our distance, so the minimum distance is approximately 0.90. And we have a 2 next door, so that will stay 0.90 unit between them. So it's less than 1, so unit would be singular. 1 or more than 1, so 1.1, 1.2, 1.3 would be units plural. So 90 hundredths of a unit away is the closest that they get. And that happens when x is approximately 0.195. Okay, so next up, we try to maximize an area. So a rectangle has one corner in quadrant 1. That is on graph of y equals 100 minus x squared. So right away we can tell some boundaries on x. If we're in quadrant 1, that means we're to the right of the y-axis, so x is positive. To stay in quadrant 1, though, the y values also have to stay positive, so x has to be 10 at the most. After 10, 10 squared is 100. Anything bigger than 10, once I square it, I'll have small number minus large number. That'll kick us into negative territory. So already we can tell our x's, we're looking at something between 0 and 10. Let's see, one corner is on the origin O. And the other points are on the axes. The other corners specifically. Alright, so we want to find a way to describe the area in terms of x, and then we'll use that to find the maximum area. Well, approximate the maximum area. So 100 minus x squared, so this is a parabola. All that shifting and translating work that we did before is coming back to kind of help us out. So the minus in front there, the squared graph is reflected about the x-axis, and plus 100 shifts everybody up 100. So we have 0, 0, and we have some point along here, x, y, and to kind of get a sense of this, why it would matter where this is as far as area, we can have different rectangles along this occupying different amounts of area. Clearly this rectangle in black is covering more area than the blue or red rectangles are. So the idea is, okay, well, how do I describe this area? So let me draw a fresh one, since I've kind of gotten that other one a little bit busy. So here's our 0, 0. We're going to find some point on here, x, y, and we're going to try to optimize that point. So that would make this point x, comma 0. Since this is a rectangle, this point then would be 0, y. Well, the area of a rectangle is just length times width, or base times height, whichever you want to call them, x times y. But again, we want to make this into a function with respect to the variable x only. So remember, they told us y was 100 minus x squared, so we'll do a little substitution, and then we have this in terms of x. So a of x is 100x minus x cubed. So once I have that, now I can go to the calculator, but we're armed with at least a little bit of that knowledge beforehand of what the x should look like. We're in Q1, so x was positive. We wanted y to stay at least above the x-axis, so that meant x was smaller than 10. So our x's are on 0 to 10 only. And we can use the calculator to figure out what we should set the y window to. But the x window, so I'll set that min to 0, and the max we'll keep it at 10. Our scale will stay as a 1, and then we'll go in and put in our 100x minus x raised to the third power. And we'll go to our table set. So second and above window there is table set. So we'll start the table at 0. And we'll change it by 1 at a crack is just fine. Delta table is just how big a step do you want to take between your starting value and the next value. I won't keep it on auto. So then we go into second and table. So our Y values, we have 0, 100, 200, 300, 375, 380s, 350s, 200s. Okay, so the highest number that I ran into there was 384, but I don't know if there are higher values around that. We're not guaranteed that a nice, neat, pretty integer is our max. So when we're setting up our window, Y min 0, and that should make sense also, just what we're talking about physically. The minimum an area can be is 0, no square footage. It can't be a negative amount of square feet. So then we'll top this out. We're into the 380 something, so rounding up to 400 would not be unreasonable. And for a gap that big, Y scale, I'll set the dashes at 20. The scale is just how often are they putting those little dots that we see. All right, so click it on there, and it does fit pretty nicely. And we want to approximate where that top is. So second and calculate, and we're looking for our maximum again. So left bound, I'm still to the left there. Hit enter. Right bound, higher values, higher values, higher values, and now they're dipping down. And a guess. So it's going to think for a minute. So there is an X and a Y. So the maximum area is 384.90, and this would be in square units. Area is always in square, volume is always in cube. Square units when X is approximately, and again we'll round that one, we have 5.77 and a 3 next door, so 5.77 units. All right, so from section 2.6, I would recommend 1 through 25 on the odds. Really with word problems, a lot of people are afraid of the word problems. There's really no substitute for just getting them done. Use your book, your notes, rewatch parts of the video, pause it, rewind it. There's really no substitute for just getting your hands dirty and trying the problems and seeing how things work out with them. Some other tips, though, that I can give you as far as word problems, particularly if you have some anxiety about word problems. There was a study done a few years back, big international study. They were studying a lot of things with education. Students from around the world were participating, and one of the countries was doing sort of head and shoulders better than other countries that had similar test scores on just the basic plug and chug type of problems, the non-word problems. If they were doing the same as their peers in that, but way better in the word problems, of course, the people running the study want to know, okay, what's happening? What are you guys doing different? And the key was they had the students read the problem first and ignore all the numbers. Kind of sounds weird coming from a math teacher to say ignore the numbers, but the first read through, ignore all the numbers, read the whole problem through, and all you want to know in the first pass reading through it is, what do they want me to know? What is it they want to find out? Then you have a goal in mind, then you're rereading it, trying to figure out, okay, what clues did they give? that would get me to that goal. Then they had them write out a sentence of, okay, this is what the answer should sound like, and just kind of filled in the blank with the number later. So you can try that out, see if that works for you, particularly, like I said, if word problems are not necessarily your favorite kind of problem. So there's some fun problems in there in this section. So see if you can give those a try. As always, get in touch with me if you need a hand, and I will see you next time.